All right, welcome to Cloud Slam 2011. This session is on research in the cloud, speeding retail innovation with live customer data. My name's Darren Vengroff. I'm from Relevance. I'm the chief scientist. And what I'll be talking about in particular today is a system we've built called RecLab. And RecLab is a system for conducting e-commerce research, particularly around recommendation systems, doing so in the cloud in a way that allows us to get context and feedback in ways that some of the traditional offline research methodologies in this area have historically been unable to do. So in terms of agenda, here's what I'm going to go through today. First, I'm going to briefly introduce Relevance and the RecLab system, what we do and what the system's all about. And then I'll review the context and data challenges that we have in the kind of recommender research that this system addresses, and why historically researchers in this area have run across problems in really replicating the kind of environment that shoppers really interact with when they're working on the web. Finally, next I'll talk about the RecLab approach and how we deal with some of these problems, how we model behavior and context, and how shoppers interact with recommendations. Talk a little bit about the computational model, how that works within the cloud, and how researchers can build systems that call our cloud APIs and run within that world. And then I'll talk a little bit about how this system has been working in the real world and some of the things we're doing to bring additional researchers online within the context of this system. So first of all, Relevance and RecLab, what are we? Well, Relevance, we are the leading provider of product recommendations for e-commerce merchants. So when you're shopping online, you see things like people who bought this product also bought that product, or people who searched for these keywords ultimately purchased the following product, that sort of thing. That's one of our main lines of business, is providing those recommendations in concert with our merchant partners using a software as a service model that runs in a distributed cloud environment. In terms of the scale that we're running within the cloud, just our top 5 merchant partners alone in aggregate are 60% larger than Amazon.com. So we're running at very significant scale and across a large number of merchants. So what is RecLab? Well, RecLab is Relevance's new approach to enabling third-party researchers, so primarily academics, but also potentially some smaller startups, to conduct research on how people interact with recommendations, to come up with new algorithms that may be more effective at driving conversion through recommendations, and to understand how those algorithms behave in the real world. And that's really the sort of key differentiator and the focus of this conversation today. So when we come up with recommendation algorithms, whether at Relevance or in the community as a whole, in academia, this is a quite popular topic within computer science research and machine learning. How do we evaluate the algorithms that we've constructed in order to make recommendations to shoppers? Well, the sort of traditional method is what I call offline metrics. They're very, very widely used. If you look in the academic literature in this field, the vast majority of papers that you'll find will use some combination of these measures. And what these really are measures of how the recommendations perform based on some fixed static data sets. So, for example, the precision and recall metrics, the way in which these are typically constructed is we'll take a data set that comes from, say, a web log of shoppers on an e-commerce site and say, what did they look at, what did they ultimately purchase, that sort of thing. And then we'll say, well, our goal is, given the behavior of shoppers, to predict what other products they'd be interested in and then recommend those. So what's done in this offline approach is we take a sample, a control group, and say, okay, let's take 10% or so of shoppers out of consideration from these log files. Let's try and build a model, a predictive model that's going to predict what shoppers will be interested in based on the other 90%. And then let's say, okay, for that test group that we held back, if we had used this model, how accurately would we have predicted what they were eventually going to purchase? Now, that's that's certainly better than nothing, and therefore it's widely used, but it doesn't really get at the interactive part of recommendations, which what we've found over the past few years in our research online is really, really critical. And there are some other offline metrics, things like diversity, which is looking at how good a job do you do of recommending a wide variety of products versus just recommending sort of a homogeneous set. Root mean squared error, that was actually at the heart of the Netflix prize. This is really trying to predict how someone would rate a particular film based on their ratings and the community ratings, and then looking at the error between what you predicted they would rate it and what they actually rated it. That has some interesting issues in that what really matters for recommendations is you have to be accurate at films that people like and rate highly. It doesn't actually matter that much if you can accurately tell the difference between a movie they hate and really, really hate. So user-centric metrics, on the other hand, these are things that you have to, by and large, really put your system in front of real users to get at. These are things like, based on the recommendations I'm making, are session lengths going up? Are click-through rates on those recommendations higher or lower than other algorithms? Do people who see these recommendations, who may be sitting at home in their pajamas shopping for video games at 2 a.m., actually buy them? Versus the behavior we see in the offline metrics that wasn't based on them actually having seen the recommendation. And then sort of the holy grail for merchants is the overall sales lift. So what we want to do is take algorithms that researchers come up with, put them in the cloud, put them in front of real shoppers, and measure these kind of metrics as opposed to the traditional offline metrics. So in the process of doing this analysis and putting these algorithms in front of people, one of the things that we've come across that's really critical to the quality of the recommendations that we make is that relevance is fundamentally contextual. And I'm going to show you a few examples of this on the next few slides, but what's relevant to a shopper changes radically from click to click. And this is yet another reason why these offline approaches really don't capture the heart of what's going on here. And so it's critical that we align recommendation algorithms and the context that they're appearing in. So here's a good example. First context that I'll talk about. This is an item page for a television on one of our merchant partners' site. So here someone's looking at this particular LG television, and the things that we're recommending are the items over here on this side, and we're saying that people who viewed this television over here on the left also viewed these other 4 televisions. So the focus here is really on discovery and comparison. This person's looking at TVs. We want to make sure that they look at other comparable TVs, particularly others that shoppers who considered this also considered. So within that context, that's a pretty good strategy. But context, as I said, can change very quickly and very radically. So look down here at the Add to Cart button. Sort of the moment someone clicks that Add to Cart button and now has this television in their cart, something very, very different is happening, and we are in a very, very different kind of scenario. Instead of trying to recommend competing TVs, they've already chosen a TV. The last thing we want to do is lead them to second guess that decision. So the competing TVs are now gone, and instead what we're showing them are accessories that have typically been purchased or that have commonly been purchased by other shoppers who bought that TV. So a Blu-ray disc player, actually a couple of different Blu-ray disc players, and some different options for mounting that on the wall. Those are the kind of things that, with that very quick change of context, suddenly we want to recommend. And so, just looking at the offline models and not knowing where someone is and what their context is, it's not such a great way to make recommendations. So if we jump ahead to another context, another kind of context is product type. So we were looking at televisions. Now let's look at two other categories, DVDs and, in this case, washing machines. If I'm buying a DVD, even if I came to buy one very, very specific DVD, I knew exactly what I wanted. It was Inception here on the left. It's not at all unreasonable for a recommendation system or the authors of a recommendation system to think that they can, given the right data, come up with a second DVD that someone here buying Inception might also be interested, in this case the A-Team. And there are any number of reasons why we might think someone buying Inception would also be interested in the A-Team. Could be behavior-based, could be genre-based, could be any number of things. But if I'm shopping for a washing machine, on the other hand, there is essentially no way that you're ever going to convince me to buy a second washing machine. I'm only going to buy a washing machine maybe once every 10 years. It's just not the kind of thing that I'm going to buy 2 or 3 of at a time. So building an algorithm that focuses on finding me a second washing machine is completely irrelevant here. Instead, I should be looking at recommending complementary products, maybe a dryer, maybe some accessories, a kit of hoses to hook it up and install it, some laundry detergent, any number of things, but almost certainly not another washing machine. That's just not going to be what I'm interested in. So now, in addition to context, there's a really critical factor in determining the quality of a recommendation system, and that's live in situ feedback from shoppers. So the research community has begun to do what are called user studies, where they'll do things like set some volunteer users down in front of a real or mocked up shopping site, have them go through and try and make some purchases. Usually they'll give the shopper a gift card of some amount to kind of motivate them to participate in the study, and they'll observe either their eye movements or their click-throughs or any number of other things, possibly stand behind a one-way mirror and watch them. But it's only really practical to do this on a few dozen users. It gets very complex and expensive to do it on any larger scale than that. So what we're really trying to do with our cloud-based approach is to enable this kind of live feedback, in addition to the kind of context that I was just talking about, for researchers with real shoppers at very large scale in the cloud. Finally, the other issue that really affects the research community in this area is data access. So production scale data sets just aren't that widely available, and there are a couple of reasons. I mean, one is that they are large and unruly and hard to move around. But even more important than that is that merchants are reluctant to share them for two reasons. One, they have competitive concerns. They don't necessarily want their competition to see how shoppers are working on their site the way that they would with a public data set. But even more important than that are privacy issues. So we certainly don't want shoppers' private behavior on a site to be made publicly available. And those issues, even when we try to do things like anonymize the data in some way by eliminating people's real names or any kind of identifying information, certainly credit card information or anything like that, and replace them with just random numbers, synthetic IDs. It's still the case that these can be de-anonymized in at least some portion of cases. And so there are, as a result, a couple of pretty well-known cases where people tried to release data sets, tried to anonymize them, and they failed pretty miserably in doing so. The first was AOL, which released a search data set a few years ago. It was anonymized. People's IDs and emails were eliminated and were replaced by anonymous IDs. And what happened is about 2 weeks or so after the data was released, the New York Times showed up on the doorstep of a woman in South Carolina, knocked on her door, and handed her a printout of everything she'd been searching for the past 6 or 8 months, and asked if that was her. Of course it was, and what they had been able to do with the help of some researchers was determine exactly who this person was by reverse engineering some of the searches they'd done and figuring out who they were. So because of that problem, these kind of anonymized data sets really just don't work well. Netflix Prize version 2 was another case where, in addition to some of the data that they released for their initial prize, which was very, very successful, they were going to add a few demographic details, things like zip code and gender of the person who was renting the films, and that created essentially the very same kind of problems that AOL ran into, and in fact the contest was abandoned before it even started for exactly those reasons. So finally, even if we were able to circumvent the privacy issues, there are still significant performance issues. So on large e-commerce sites, in order to build these models, you have to be able to consume billions of raw data points, even tens of billions or more. And you also have to be able to support runtime calls that actually get these recommendations out of your models very, very quickly. So we can't have users that are being exposed to a test algorithm exposed to really long delays in delivering their recommendations. The lack of responsiveness could actually offset the benefit of these improved recommendation algorithms. So this is yet another reason why a cloud environment is really ideal for hosting the kind of experimental recommendation systems we're talking about. Researchers typically don't, within their own laboratories, have the kind of production infrastructure that can either scale out to this size of data or deliver these recommendations in a live shopping environment as quickly as we have to. So given all these problems, how do we solve them? Well, the sort of fundamental underpinning of the RecLab approach is that we say, if you can't bring the data to the code, bring the code to the data. So in other words, if for all the reasons that I just outlined, it's simply not feasible to take these very large data sets that we at Rich Relevance have in our cloud that we're gathering every day from our merchant partners from live traffic on their site and give those to researchers so that they can run their load them up into their algorithms and run them. Then instead, let's find a way that we can take these clever new algorithms that these researchers are coming up with and bring them into our cloud where they can operate on this data, where they can run on it in a secure environment that doesn't expose the data to the privacy and competitive concerns that I just outlined, and also that has the kind of cloud-based computing horsepower to actually allow them to process all of this data, all of the context that's so critical to building good models, and then run live and get the kind of feedback that's really necessary to address the performance analysis side of things. So really, essentially, solve all of the problems that I outlined earlier in one fell swoop. So what are we specifically doing with RecLab? Well, the first thing is we provide APIs that allow the researchers to do the two critical pieces of recommendations. First, to access the data and build models. So we provide them a very well-documented API that explains exactly what format the data comes in, how they can access it, and so on. And then we provide an environment with billions of real data points where through that API their models can be built. We solve the second half of this by providing runtime APIs that, given the models that they've produced, are able to serve recommendations to live shoppers, again, entirely within our secure cloud. So all of this happens in production scale anyway, within our cloud. So in order to develop and debug the algorithms before we give them real data and live traffic, we've provided a synthetic environment and some synthetic data for development debugging purposes. So this is something that researchers can download and run at small scale on their own systems. It's not real data. It's data that has some statistical similarities to real data, but it's absolutely not real users, with obfuscated IDs. It's totally synthetic. So what this does is gives them an opportunity to debug things, make sure that their algorithm does basically what they expect it to for well-known cases, and then they can upload the code to our environment, and after receiving our approval, run that in partnership with one of our merchants on live data, on live traffic. So what exact data do we make available to them within the cloud? Well, essentially what we make available is the full clickstream of all the sessions that have happened on a particular site for a fairly long period of time, period of weeks to months. And that clickstream has everything that shoppers do within their sessions on the site. They visit the home page, they visit category pages, they do searches, they visit item pages, they add things to their cart, they purchase items, they rate items, and so on. And it's annotated with additional data, so the timestamp, when did a particular event happen, and then things like the user ID and session ID. So what was the ID of the shopper? What was their session ID? And these things, we don't have to have the concerns that I was outlining earlier around privacy, because this is all happening within our cloud. This code is running within a secure sandbox where it can't just it can look at these behaviors and it can build models, but those models never leave the secure environment. And the code can't go and reach out and open a network connection and dump this data out. It's in a locked down, secure section of our cloud. Other things that come along with the data, things like search terms, search results, items added to cart, what's in the cart in any given context. So you may not actually be on the cart page right now. You may be somewhere else on the site, but what's already in your cart may have some bearing on what it makes sense to recommend to you. In terms of how we access the data and what the performance looks like, the synthetic test data that I was mentioning, that actually includes tens of millions of data points, but our code and APIs are efficient enough that this can run effectively on a single machine. So a lot of the models will build in literally just a minute or two, sometimes well under that on a single researcher's machine. The production model builds, though, where we're dealing with orders of magnitude more data, those happen within the Rich Relevance cloud fleet, and therefore those computing resources through our cloud are made available to the researchers whose code is running in that environment. The production runtime is served by our, again, cloud-based distributed low latency architecture. So we do all the standard things that people do in clouds to ensure low latency access to end users. Our cloud is distributed across 7 physical locations in the U.S. and Europe, so there's always a piece of that cloud that's close to the end user. So we have got this scale and we've got this distribution that enables us to really look at the performance of the recommendation system and not have to worry about how some small-scale research system within a lab somewhere is connected remotely to a server environment and then eventually to the end user and is introducing delay or other factors or availability issues that could affect the results of our experiment. Private data remains private and secure. As I mentioned, none of that data ever leaves our cloud environment. The overall performance is aggregated, and we can tell researchers things like, relative to existing rich relevance algorithms, your recommendations generated 3% more sales, or 5% longer sessions, or 5% lower sales, as the case may be. But we're not telling them anything about what happened with a particular user. That never leaves the cloud. So all of that really enables us to solve these problems that I was mentioning earlier, and bring researchers both from academia and other small companies into this environment in a way that in the pre-cloud era and in the absence of these cloud-based APIs just simply wouldn't have been possible, and for that reason has never happened before this RecLab system went live a few months ago. In terms of developer support, what do we provide for people who are interested in getting involved in this and building algorithms and tools in order to run within our environment? Well, first of all, we provide a familiar MapReduce programming model. So MapReduce is a very popular paradigm these days. Widely used within cloud environments at Google, where it was originally developed, and at Amazon, other clouds as well within our world. And then there's a very popular open source implementation called Hadoop that many people are familiar with. We provide detailed tutorials and examples. I'll at the end of the presentation give you a URL that points you to where you can access all of that. Quick start on a single machine with no configuration, so there aren't pages and pages of XML configuration files that you have to edit. You can literally, by following the tutorial, have the first example up and running in minutes. That's assuming you don't dig through the source code you download, but if you do, you can still certainly quickly understand exactly what that code you downloaded and ran in 5 minutes is doing in an hour or so. We provide the synthetic data sets that I mentioned for testing purposes. Those are provided in a human-readable format, so it's YAML, which is it's not XML, but it stands for yet another markup language. It's a little bit simpler and easier to read. It also makes it easy for researchers who may have their own data sets that they've collected to convert them into this format, verify that the algorithms that they've written within our APIs produce the same results as versions they may have implemented independently. It's a good cross-check. We even provide some utilities to convert from some other common research data formats to help in that effort. All of the code and APIs are available in open source form under the Apache 2 license, so there's not really anything to worry about in terms of that code being our proprietary code and something that is difficult or challenging to integrate into other systems. So it's a very easy way for researchers within this field to get at the kind of large-scale data and user feedback without having to learn a whole new computing paradigm, and without having to use some ill-documented piece of code or APIs that they have downloaded from the web. So that's really the problem that this cloud environment that we've built to support both our own operations and now the RecLab that we're opening up have enabled us to solve some of these traditional problems in this space. So coming up, actually, early next month, we'll be announcing on top of the RecLab system the RecLab Prize. So this is basically a very significant prize, something along the lines of the Netflix prize that I mentioned earlier, and that many of you have undoubtedly heard about and followed through its few years of run. But we'll be offering a large cash prize to academics and research teams and the institutions behind them if they're able to use this system to generate significant lift, so generate significant increases in sales, and the exact details and thresholds and so on will come out in the rules that we'll be announcing next month. But it's an opportunity to win a pretty significant prize, in addition to an opportunity to get your research code in front of real users and real shoppers. So we're very excited about that, and as I said, the details are just a few weeks away from being announced. All right, so finally, I guess I will wrap things up and move on to the question and answer period. Want to thank all of you very much for attending, and also point you towards the website where you can find the APIs, the documents on those, more description of how the system works, and also download some of the code that enables you to write recommendation systems based on these APIs. You can also follow us on Twitter at RecLabs, Also, we have a couple of different mailing lists you can sign up for on the website for additional announcements or for discussions of the technology behind RecLab. So thank you very much. And if the Q&A system is working, which I believe it is, I'd now be happy to take your questions. The way this works is there's a Q&A section on the lower right corner of your WebEx Event Center, and you can type questions there. I'll repeat them verbally so that everyone else on the line gets a chance to hear them, and then I'd be happy to answer them. So if there are any questions, by all means, please let me know. All right, I'll wait another minute or so for any questions to roll in case there are some of you that are frantically typing them right now. But I'll give you another minute or so. All right, well, I guess I will sign off then, and thank all of you for attending, and have a happy Easter this weekend for all of you out there. And I will, if you have any further questions, comments, by all means shoot them my way via one of the email lists on our website. And thank you very much.